Hello, good morning everyone. So today we are going to discuss about how to interface, uh, how to program STM32 using we will be using embedded C. Uh, it's embedded C. So to start off with, there are three major points. First thing is STM32 has many registers, and second thing is it is a ARM Cortex 4 microcontroller, Cortex M4 microcontroller. So in order to program this, you have to configure many registers. So in the course of programming this STM32 using embedded C, we will be using STM32F401 RETX as our target microcontroller, and we will be also using this reference guide for this in order to program this STM32 microcontroller. So without any further delay, let us move on to how to program this. First we have to install MDK ARM for Keil, as I have shown in the previous video. So after installing, if you open Keil, the recent project that you have worked on will be popped up. So you have to go to the project section. You have to create a new microvision project. It will ask for a title, create a folder, uh, create a folder with the project name. Like, let's say now we are doing simple LED toggle. So okay, LED toggle. So in that you create a project name LED underscore toggle. So project will be created. It will ask for the target microcontroller. So our target microcontroller is STM32 F401 RET. So this is our target microcontroller. We have to click on OK. Once we click on OK, there will be a window popped up like this. Here you have to select CMSys. In that you have to enable core, and in device section you have to enable startup, and then you have to click on OK. If you see now, you can see in the project window that LED underscore toggle project has been created with a startup code, which has startup file which has been included. And in order to write an embedded C program, you have to right click on the source group, and you have to select the second option which says add new item to the group, and in that you have to select the file type as C. Now let us name this as LED underscore 1, and you have to add it to the project. So before moving into programming it, I'll tell you where to find the reference manual of this. Here you can see in the below the project pane, if you closely observe, there is something known as books. So if you click on it, it will show you STM32 F401X reference manual. So if you double click on it, it will take you to the reference manual. So we'll visit this later. Now let me tell you how to start with. So you have to first include the directory, which is hash include stm32 f401xe.h. Here we are using x4 stm32 f401re, but we are using the library stm32 f401xe.h. Now the main thing is how to start. So first you have to open a main function, and then I'll tell you the flow. So in STM32, to start off with, you have to enable, wait, let me clear everything. So yeah, in STM32, to start off, you have basically two things. Enable clock first. Clock to whom? You have to enable clock to all the peripherals that you are using. If you go to the data sheet, sorry, reference manual, there you can see that the clock will be set by a register called RCC, reset and clock control register. So using this register you can set any clock, and after setting the clock, while enabling the clock, you have to make sure that the clock is enabled to all the peripherals you are using. And once the clock is enabled, you have to configure respective registers. So in our case now, we are thinking of so in our case now we are thinking of starting with a simple LED toggle. So for that, what we need, we have to first enable the clock. Clock to what? Clock to GPIOs, and then configure a particular GPIO pin as output, and then set and reset that particular pin with some delay. So now let us do this one by one. So okay, first we have to think about enabling clock. Now we'll move to the reference manual. Here if you see, there are many sections in the reference manual. Here you have to search for real-time clock. Not real-time clock. Real-time clock is something which is crystal oscillating at 32.76 kilohertz, which is used for holding the real-time clock, which is normal time, which is like 7:30, 8:30 regular time. So coming to what we need, if you see the sixth section, reset and clock control, RCC. So if you go there, there is something called RCC registers. If you go into that, you can see there are so many things: RCC PLL configuration, RCC clock interrupt configuration, RCC AHB1 peripheral reset register, AHB2 peripheral reset register. So but what we are interested in, we are interested in peripheral clock enable register, which is RCC AHB1 peripheral clock enable register. So here you can see RCC AHB1 peripheral clock enable register. If you go there, you can see there, here if you closely observe, it is mentioned GPIO enable, GPIO D enable, GPIO C enable, GPIO B enable and A enable. So basically what is this is, STM32 has 4 GPIO ports. So if we shift back, let me tell you. So yeah, so STM32 has 4 GPIO ports, A, B, C, D. So in order to toggle a simple LED, now let us say we are using port A.5. There is some specific reason I have selected this, because if anyone are using Nucleo board is for STM32, according to the board schematic, the user LED is connected to PA.5 pin of the STM32 target microcontroller. So now we will be using this STM32 PA.5 for developing a simple LED toggle code. So as I have mentioned, there are 4 GPIO ports. You have to enable clock to only GPIO A, and after enabling clock you have to configure the particular GPIO. So first let us shift to enabling clock. So in the first line you will be writing RCC, and in STM and in embedded C, these all the registers are type def structures, so you have to access their members using an arrow operator. So if you click on arrows, you can see that AHB1 ENR, and you have to assign this with, if you go back to the reference manual, in order to enable clock to GPIO A, you have to make the last bit as 1. Remaining bits are not of your concern, so you have to make it as just 1. So you have to assign this with 1. Once you are done with enabling clock, the next thing left is you have to configure the GPIOs. So in order to configure GPIOs, you go back to the reference manual and you check for the GPIO section. If you check for the GPIO section, here if you can see, there is something called general purpose IOs. In general purpose IOs, if you are interested, you can really go through this GPIO introduction and main features. This will give you a good introduction about how to configure registers and what happens if you configure the particular registers in a particular way. It is clearly written here. You have to go to GPIO registers. In GPIO registers, in order to configure GPIO registers, there are some steps. So first you have to make sure that mode register is configured, and after the mode register is configured, based on whether you are using it as input or output, you have to either read data from IDR, input data register, or if you are using it as an output, you have to write data to output data register. So once you are done with configuring the mode register and reading or writing ODR, we will be taking care in the next part. So first thing is you have to configure the mode register. You go back to the reference manual. Here the first thing you see is GPIO port mode register. So there is nothing to remember, you have to read the reference manual. So here if you can see, if you write 01, the default mode will be output mode. If you write 10, alternate function mode, 11 analog mode, 00 input mode. So before writing, before configuring this, you have to make sure that you are populating this register with its default value first. So first you have to reset the register, and after resetting you have to configure it. So if you see, the reset value is 0xC000000. So you go back and you have to write GPIO-A. From that I am configuring the moder register with its default value, which is 0x0C00 and 4 zeros. Yeah, and after the default value, now you will be configuring the actual value, which is GPIO-A. Now you need to configure the moder with what value. So as I have mentioned earlier, we are using port A.5, which is, if you consider this as port A.0, 1, 2, 3, 4, 5. So this is port A.5. So in order to make this as output, you have to keep the bits as 0 and 1. For writing it in hexadecimal format, you consider 4 bits as a single hexadecimal bit. So these 4 will be a 0, these 4 will be a 0, and in moder 5 we will be writing 0, 1. So until moder, for moder 0, moder 1, this will be a bit 0. And so if you now closely look, now the moder 0 is configured as input, I mean by a default reset state, and 1 is also default reset state, 2 is default reset, 3 default reset, 4 default reset, and PA.5 it is configured to be an output mode, so it should be 0, 1. Now we have to divide everything into a hexadecimal format. So for that you can directly divide this into groups of 4. So this will result in a 0, 0, and this will result in a 4. So the configuration will be 0x, 4 zeros, and another 0, 4, 00. So this will be your final model register configuration. You have to go back to the Keil and configure it with 0x 400. So now we are done with configuring. Once you are done with configuring, the next thing left is you have to populate the ODR. Now let us see how to do that. You have to go back to the reference manual. You can erase this, and here you can see in the GPIO section, after modder there is something called input data register and output data register. You click on output data register, you see the upper 16 bits is reserved, and in the lower 16 bit, for every particular pin of the GPIO there is a bit reserved. So either you set or reset, this will be reflected there. We want 0 PA.5, so we will be configuring the fifth bit for 1 for some time, give a delay, and make it 0, give a delay, and make it 1. So we are only interested in this bit. So remaining by default, let us keep them as zeros. So again the same thing, you have to group them 4 bits. For every 4 bits you have to group them as 1, and yeah, so it will be 20. So you will be constantly changing the ODR value between 0x and 0x 1 2 3 4 5 6 7 8. You'll be constantly changing the ODR values between these two. So for that, the first thing you have to do is you have to start with a while loop, infinitely non-ending while loop. In that you have to go to the GPIO modder, GPIO A ODR. You will be initially making it as 0x 20. Check the number of bits properly, yeah, and then we will write some delay function. Let us say the delay function name is make delay, or a simple delay of, let's say, let us take an integer input of, let's say, 30, and then we will be making the GPIO A ODR back to its normal state, which is 0x, and then again we have to call the delay function. In everybody, please don't forget, this is a normal embedded C coding similar to C, so we will be using only C basics. So in order to define the function, you have to define its prototype first. So void delay of int, this is the prototype, and this is the function implementation, delay of int k. Let me write a simple for loop. Int I, you can give any number here, like based on your convenience. You can write a normal return statement. So now you are done with the whole program for toggling a simple LED. Now the next thing left is you have to compile this. So before compiling, you have to go to the flash and configure flash tools. In this you have to go to the output section, wherein you have to tick the create hex file section, and here you can rename the file name as LED toggle underscore hex, so that you can easily identify it. And you also need to go to the debug, and for debugging you have to change it to the use simulator and click on OK. Now once everything is done, you can click translate, which is in the left corner, if you can see. So it will use the compiler and give you if there are any warnings or errors. You can observe there are no warnings and errors, and then you have to go to the build. You can see that creating hex file, and hex file is being created. Now let us see how to implement this, like how this code is working in Proteus. If you are familiar with Proteus, you can open Proteus and click P. It will open a pick devices window. There you have to select STM32F401 RET. So you can see there is a microcontroller with this name. You can place it here. Now the thing you need is a simple LED. Let us take a red color LED. Yeah, so as a good practice, make sure you are using it as a using microcontroller as a sink rather than as a source, because that might damage your pins. So go to the terminals, there you pick the power, place the power, route it, and now you need to double click on the microcontroller, navigate to where the project has been saved. If you can see, there is a LED toggle. In that you have to go to objects. In objects you can see there is a hex file located. You have to click on open and click on OK. Now after everything is done, you have to click on simulate, which is located in the bottom left corner. You can see the LED is blinking. So if you want to reduce the increase the interval of blinking, you can go back to your Keil workspace and change it to, let us say, 50 instead of 30, so that it will be clearly visible, or maybe 70, and you can do the same here. And the same process, compile and then build it. Once the hex file is established, go back to Proteus, stop the current simulation, double click, and here you in the place of program file you have to select the hex file again, because it will be changed this time. Now click on OK and click on simulate again. You can see the blinking time has been increased. So this is a basic embedded C application to start off, wherein you are blinking a simple LED that is connected to PA.5. So yeah, so if you observe steps from beginning, you will be enabling the clock, configure the particular GPIO pin as an output or input, set and reset with particular pin with some delay. This is the standard process for any to develop any application, at least for ARM based microcontrollers. Thank you. And I'll be explaining more interfacing videos, like how to interface a switch with STM32, interfacing a 7-segment LED in the upcoming videos. So please don't miss them. Thank you.